So today's guest is Professor Yale Pat, who is the Professor of Electrical and Computer Engineering and the Ernest Cockrell Jr. Centennial Chair in Engineering at the University of Texas at Austin. Professor Pat is truly a giant in the field of computer architecture, having won the highest honors in both research and teaching. He's also co-author of our textbook, which is Introduction to Computing Systems, From Bits and Gates to C and Beyond. And Yale, we're very grateful that you could come by today.
It's a pleasure to be here.
So I'd like to talk a little bit about the book. So I think it's really a fabulous introduction to computing. You know, many students here at Cornell and many more taking this course have learned about computing through this book. So you're a very busy person. You've got a lot of things. You've got a big group of graduate students, and you found the time, and you were very motivated to write this book. So what kind of motivated you to write this particular textbook?
The fact is that most students are being introduced to computing incorrectly. In fact, most of the kids you get here in the freshman year have taken computer science in high school, where they've been taught Java, which is a language where the language is such that you can be totally unaware of what's going on and still get the program to work, because the system will protect you from yourself. Mm-hmm. And so you don't really understand what you're doing, but you can get it to work. And I've always felt that starting with something at a high level where you have no idea what's going on is a big mistake. And in fact, the mistake is that what the kids do is they end up memorizing everything. And they hope that they've memorized a pattern that they can then plug in. And they just keep memorizing as they work from the top all the way down to the bottom. I said it'd be a lot better if they started at the bottom. Okay? And there's just a very few simple concepts. In fact, you know the book, so you know that we start with a light switch. In fact, a light switch is very similar to a transistor in its behavior. And kids have been doing light switches since they were 2 years old. So if you tell the kid, you know, you do this, the light goes on, you do this, the light goes off, you know, that doesn't throw them. I mean, they've been doing it since they were 2 years old. So that's where we start. And we use that and we build. So from transistors, we build gates. And from gates, we build muxes and decoders and memory, as you know. And then from there, we build a computer. And from there, we program the computer in its own language. In fact, the first program is written in zeros and ones. And then once they master that, then we write the program in assembly language. And then once they master that, we write the program in a high-level language. So we're constantly building on what they know, raising the level of abstraction. Raising the level of abstraction is good, providing you understand what's going on underneath. And so I felt that this was the way to build the foundation that they need. And education is all about building a strong foundation.
Now, I understand that the book has been used at over 100 universities around the world. So what are some of the places that it's been used?
So the Chinese have bought into it big time. So it turns out that that's a good question, actually. In fact, I should get the list to see how many are in the U.S. and how many are in, you know, other parts of the world. It's used at different kinds of universities. So, for example, it's used at elite universities like Cornell. It's also used at some of these, you know, fifth-rate universities. It's used at places where they feel the right answer is to build on what you know rather than memorize. In fact, I don't know whether you've ever seen my 10 Commandments of Good Teaching, but one of them is
I have seen those.
Emphasize learning, not memorizing, you know, because, you know, we're engineers. We solve problems. We don't memorize. Nobody wants you to memorize and then solve the problem you solved yesterday. You want to solve the new problem, and the way you do that is by memorizing. It's China is probably the best example. So the book has been translated into Spanish and Chinese.
So I want to talk a little bit about the LC3 instruction set.
Sure.
Which I think is, you know, a very powerful instruction set, and that you can do so much with it. But it's very simple, easy to understand. So can you talk about how your kind of dual role of educator and architect came together to create the LC3?
Yeah. So I suspect that I would not. So the LC3 didn't happen just like that. You know, I mean, I thought about what do I want to put in this instruction set. And I have the benefit of being an architect now for what, 50 years? And so I've seen a lot of computers. And so every computer, the instruction set is a little bit different. Some of them are very different. And so I could draw on what they do to say what's important to put in here. And my, in fact, I'm flattered that you think that the instruction set is simple and yet rich, because that was exactly what I wanted. I've seen some computers where the instruction set is rich, but it's a nightmare for the student to try to master it. There's just too much he has to memorize. I didn't want that. I wanted an instruction set that would fit. In fact, you've got the book. If you look at the inside cover, you'll see the formats of all the instructions. It's sufficiently simple that the kid can grab it all in his brain with very little effort. Right? And I wanted that. At the same time, I didn't want to have just a Mickey Mouse, a simple instruction set in the sense that you couldn't do anything with it. So I very carefully put in instructions that mattered. And so even though there's less than 16 opcodes, it's a rich set. So it's a rich set, but yet the number is small, which allows the student to grok. You understand the, Vonnegut's word grok. Grok the instruction set. And no, it didn't come out overnight. I worked on it. In fact, the instruction set from the LC, so the LC3 is because the LC1, LC by the way is little computer.
Right.
And when I was at Berkeley and taught the architecture course, I needed a little computer to have them implement. That was the LC1. Impossible to program. It just had one register, an accumulator, Ugh. So when I taught the course the first time, I introduced the LC2. Well, I got it wrong again, see, because I did things badly, and so now I think I got it. The LC2.
Three's a charm.
I think 3 is a charm, actually, because then the next edition will not change the instruction set.
Now you picked 16 bits, right? You could have picked, there are 8-bit machines, right? There's a lot of 32-bit machines, right?
Most
a lot
of
of
them are
smartphones
30. No,
are 32-bit.
most of the instruction set.
But you picked, well, that's the size of an integer, but you also picked instruction size that was 16 bits.
I would say,
instance.
so most of the, I think this is true, that most of the fixed length instructions are 32 bits.
That's right.
Now there's the x86, which is variable length, as you know.
Right.
But most of the fixed length instructions are 32-bit instructions.
Yep.
There's a danger, if you have 32 bits, you're going to want to use them. 8 bits is too Mickey Mouse. There's nothing you can do with an 8-bit instruction, although there have been some designs for pedagogical reasons that used 8-bit instructions. What I wanted was something was big enough that it could be useful, that you could actually sink your teeth into it, but not be so big that it was going to... I am big on doing such that the student can get it without memorizing, or with a minimum amount of memorizing, and 16 bits just felt right to me, and it restricted me to a 4-bit opcode, which means
right.
only a maximum of 2 to the 4th or 16 opcodes. I've seen, in fact, there's a popular textbook in computer architecture that uses a pedagogical machine, and the author of the textbook did not write the textbook for that pedagogical machine. Another guy did, and it goes on, and the kid can't master it. It just there's too much there. With a 16-bit instruction, you can sort of work it in your head. You can look at 16 bits. 32 bits is just too many. So I felt that 16 was and I'm delighted with the that I got it right. 16 bits is right.
Now you said you have 4 opcodes, right? So you have
4
bits. I'm sorry, 4
right,
bits for an opcode. So, but one is reserved, right?
That's
so
right.
People might wonder, like, why not use all 16? Why do you have like one opcode that's unused?
So it turns out I had 16 opcodes, and so as you pointed out, and I also reiterated, that it's a rich instruction set, even though it's a very small instruction set. In that instruction set is a subroutine call return mechanism, which you have to do for richness, right? And I had a call instruction, JSR, jump to subroutine, and I had a return instruction. In fact, curiously, and I didn't realize it at the time, but my call return mechanism is the same as what ARM introduced when they introduced their ARM version 1, a long time ago. So You know, brilliant minds think alike, as they say. The call return mechanism works by the call instruction. So when you call a procedure or subroutine, program is running. And now what you do is you want to do this extra piece of work. So there is an instruction that says, go there and do this piece of work. And when you get done, come back. Come back where? To the place where you came from. So you have to save that location someplace. And I save it in register 7. I don't know where ARM saves it in the register also. So the call saying, go do this piece of work, also has to save that address to come back to. You get done, and you want to jump, that is, come back to here, and the instruction that does that is the same as the jump instruction. Mm-hmm. So I'm lecturing to this class of freshmen, and there's 400 of them out there, and this kid raises his hand, and he says, why do you have the return instruction? Why don't you just use the standard jump instruction, which is another one of your instructions, only identify which register in the instruction, and now you've got the return, and you don't need the return opcode. You've saved yourself an opcode. And I'm up there, and wow, that's brilliant, you know, and of course I did it. Now there's a side note to this, by the way, that this was like 10 years ago, I guess, right? No, more than that, because the book came out in 2004, so it was probably, you know, 11, 12 years ago. Every time that kid has needed a letter of recommendation, he has reminded me that he was the freshman.
He was the one who taught you about your instruction set.
He's the one that taught me that I didn't need a return instruction. So I got 15 now, so what do I do with the other opcode? And I decided, you know, let me just leave it for future use. I'm a good engineer, right? Contingency. Leave it for future use.
So one of the ideas that you mentioned is your work in asymmetric chip multiprocessors, which probably people know more about as multicores and heterogeneous multicores. So,
those are all the right buzzwords.
Right. So why is it important to have cores that are not alike, cores that are different capabilities on a chip?
Yeah, so there are, companies, so I've been talking about heterogeneous for a long time now. It's been, I came up with the notion, what probably wasn't the first one, but it hit me, in fact it hit me in a talk I gave at Illinois back in 2002, so that's 12 years ago, that you really want heterogeneous cores. And at that time, in fact, up until about a couple of years ago, all the multi-core chips, multi-core, as you know, a core is a processor. In the old days, the chip had one processor on it, so it was, you know, a single core. They didn't call it cores then, they called it processors. And then, and in fact, I don't know why they call it cores, but we seem to be stuck with that in our lexicon. We then went to 2 cores on it, 2 processors on a chip, and 4 and 8. And it's easy to do if, in fact, they're identical. Because when you do the design, you do one design, and you bump, bump, bump. It's like a cookie, making cookies with a cookie cutter, you know. They're all identical. So it's cheaper because you only have to design it once. If you do heterogeneous, if each one of them are different, then it's not so easy because you have to have a design team doing one, a design team doing another, and a third one. And you say, well, does that make sense? Well, I got a couple of analogies for you. Many people have a machine shop in their basement where they do carpentry and fix things and fix your car and all that. And you need a set of wrenches. Well, you don't really need a set of wrenches. You could have just one wrench, adjustable wrench, right? And then you just set the adjustable wrench to whatever setting you need. What if that bolt is rusted on? The adjustable wrench with slippage, you'll never get it off. But with a set of wrenches, each wrench has an individual size opening, and you need the one of the wrenches for the particular bolt. And there are many different bolts, and so you need many different wrenches. You could get away with a single wrench that's adjustable, but it wouldn't work as well. And that's always the case, that if you have something to design for a specific task, you'll do much better on that task. Problem is, of course, you can't do any other task with that. So the wrench that has an opening of 1 inch is useless on a 2-inch bolt or a 1/2-inch bolt. Don't work on either. It only works on the 1-inch bolt. But it really works on the 1-inch bolt. So if you want to optimize the performance, you need something tailored to it. Another example is I gave you one football analogy. Here's another football analogy, right? So how many quarterbacks do you want on the team? You know, how many wide receivers? How many field goal kickers? You know, in fact, if the team was made up of all field goal kickers, you know, these skinny kids that would break in two, you know, the other team would run all over you, right? Or, and in fact, a football team, 11 guys on the field, and every one of them is a heterogeneous set. You've got one quarterback. You know.
Set of specialists, right?
That's correct. He's a specialist, and he's tuned. You know, when we grow a quarterback, we grow him different than when we grow a offensive tackle. And if you put the two of them side by side, it wouldn't be difficult to recognize which is the quarterback and which is the offensive tackle, right? And that's the thing, is that anytime you want to optimize, you want a special purpose thing that is optimized for that thing. So it made sense to me, well, as I say, 12 years ago, that we ought to do that. That is, if we have a chip with multiple processors, they ought to be tailored to their specific needs. Now, the thing I was flying in the face of, which is, and now everybody seems to agree with me, and it's not me, I mean, I'm not the only one that thought this way, you know, years ago, but the prevailing wisdom was too expensive. If you only have one, you can have multiple by going boom, 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 and it's much cheaper to do that. So I've been pushing heterogeneous forever, and now pretty much the industry seems to agree that heterogeneous is the way to go.
But it creates a lot of problems, right? Because it's easy when you have homogeneous cores to determine if I have a bunch of tasks, I can just put them on any core.
That's
right?
correct.
So now you've got all of these specialists, and I have all of these different tasks. So how do I deal with the fact that
you need a great
I have to
coach.
mix and match?
You need a great coach, see? The coach would never send in the kicker to be the quarterback, see? And so what you need is, and in fact, I've been advocating having on the chip some functionality that would determine when you need to send this task to which core. So in fact, this ACMP that I came up with, I guess it's about 6-7 years ago now, has a heavyweight core that is one that is very powerful, and then these very simple cores. And the nature of the application determines where that task ought to go. And so I need some resource manager, and I like to think of it as what we call the runtime system, which typically is thought of as part of the operating system, which is way up here, have it right on the chip, getting information from the use of the resources on the chip to determine where to go. In fact, so somebody showed me this, so another analogy, they have this, where was I? Can't remember whether it was in Israel or whether it was in Spain. There's some GPS system, maybe you know about this, where it is so good that as you're driving along, they will monitor the traffic patterns on the alternate roads, and your route will be determined dynamically. So you're sitting in your office and you say, I got to get to such and such. So you get out the map and you plot the path. You get in your car and you drive there. There's an accident halfway. So you sit there for 3 hours waiting for them to clear the debris, right?
Right.
No, if you know the city, when you see the accident up ahead, you go around it. So you never have to wait, okay? Difference between doing it before you start, which we call statically, and doing it as you're doing it, adjusting, which we call dynamically.
And that's at runtime.
That's right, at runtime. In fact, that's what we call it. Compile time is done before you start. In fact, that's changing also. Runtime is as you're doing it, dynamically. So somebody told me that there's now a GPS system, you may know all about this, I don't, where instead of the path being determined by somebody at the factory who programmed the thing in the first place, the there are sensors out there that are sampling, you know about this? Sampling
They'll dynamically route you.
That's right. They're looking at, well, if you go this way, you're going to get into a traffic jam. Maybe it's an accident, maybe who knows what it is. You go this way, there's no cars on the road. And they will dynamically adjust accordingly. And I think that's, you know, that's the way to do it. And so I'd like to take that resource manager thing, put it on the chip. It's getting monitoring information from the chip. You know, this is busy, don't send it there. And have it adjust to which core gets the work to be done, you know.
Now, you also talked yesterday about what you called morph core, which is a core that can morph between being a very complicated superscalar, out-of-order machine with very
Heavyweight,
complicated
right,
branch
absolutely.
prediction, and you can dynamically morph this into, say, a set of smaller cores, which are simpler.
That's correct.
And this seems to make a lot of sense, because if I have one thread that I need to get done as fast as possible, I can use the big core.
Right.
ILP, I can exploit ILP. But if I have multiple threads and I have TLP,
Right.
then I can exploit that too. So,
And the third thing is, if you have no LP, then you can just use one of the Mickey Mouse pieces of it and let the rest of it just be powered off and
Right.
not waste energy.
Be energy
That's right.
efficient.
Yeah,
Right,
that's
right.
Yeah.
But there's this kind of tension, right, with this configurability versus efficiency.
That's
can
absolutely
Can
correct.
you talk a little bit about that?
Sure. So the student who just finished his PhD last May, I guess it was, and he's now taking a job at Apple designing a processor. And he wanted to make every core on the chip a morph core because you never know. He says, well, maybe you need all heavyweights. So you're absolutely right. Anytime you put flexibility in, you're going to lose in performance. My adjustable wrench thing, you know, the adjustable wrench is flexible. You can use it instead of every one of those wrenches. You don't need 10 wrenches, one will do. But the 10, for any given task, the correct one of the 10 is better than the adjustable wrench. So anytime you introduce flexibility, you will not do as well as if you tailor it. So why is morph core a good idea? Because it provides a flexibility. What's wrong with it? You can't get the optimal performance for the task. So for example, if in fact you have ILP, that is, you need a heavyweight core, you don't have as heavyweight a core as if you designed it just as a heavyweight core. But it may be that you need 3 or 4 heavyweight cores at one point. How many do you design into the chip? If you design it into the chip, you've got these 3 or 4 heavyweight cores, and if you don't need it, you're wasting a lot of energy using it. In fact, our first work with ACMP was 1 heavyweight core. And with 1 heavyweight core, we discovered that, gee, you know, there are times we need 2. We didn't have 2, we had 1. What Chabed, my student, would say is, see, if we had had 2 morph cores, then when we needed 2, we could have 2. Now, my view of the chip of the future is you're not going to have all morph cores. I think he's wrong. You're not going to have all heavyweight Mickey Mouse. I think that's wrong. What you're going to have is some heavyweight designed as heavyweight so that you can get that ultimate performance, many Mickey Mouse so you can get that minimum energy.
Very simple cores.
That's right. So yeah, I use the word Mickey Mouse, and Mickey Mouse equals simple, and it's fun actually to go to a conference now and have people who were never trained by me use the word Mickey Mouse, and my students sitting in the audience, they laugh. They say, "Wow, so he's adopted your name for it," which is kind of fun. But and then several morph cores. So if you need more heavyweights than what you've designed as heavyweight, you've got this extra capability.
Right.
And so you like the flexibility, but every time you go with flexibility, you're going to lose on either performance for heavyweight or energy savings for simple. I'll use your term, simple. Right?
But the key to doing this is to have a runtime system, right? That can monitor what's going on dynamically. Right? It's a dynamic system where you're monitoring performance, monitoring power, monitoring the different applications, and trying to arrange things in the optimum way.
That's correct. In fact, you know, in my talk yesterday, there was a slide where, and in fact, I didn't realize it until I prepared that slide. I was looking for examples of when the runtime system makes sense. And it turns out I know, it's amazing that I've been doing this for years and had no idea I was doing it. But I looked at the dissertations of my last 4 or 5 PhD students, and every one of them is doing some variation on, so the latest PhD, the lagging threads, you know, that's monitoring. You've got multiple threads that are working concurrently on these multiple cores, and one is slower than the rest of them, you know. And they can't all go forward until they all get to a certain point. So the monitoring says take the slower one and put it on the heavyweight so it'll get done, you know, faster. And it's another example of this, of monitoring dynamically so as to provide the resources that are needed dynamically so to get the job done. You know, it's kind of like the airplane is not able to take off until the passengers get on board. And the passengers came in on a different flight. So they have to get from the gate they came in to the gate that they go out, see? And there are a couple of passengers that are either old or slow or have a bum knee or something or other. And if we have to wait for them to get all the way, the plane's going to leave a half hour late. So what we do is we provide a heavyweight core. It's the cart that you put the person on and boom, he goes to the destination and he gets there in time. So you've used the cart. The cart is a heavyweight core to take care of this lagging passenger who would take too long to get there. So this concept of dynamically allowing the usage so that the whole job gets done faster is, you know, we do it every day at airports. So it's.
And this is an example of, you talked about synchronization in a way, right? Because all the people who could be the threads are waiting for this slow thread, right? So we need to assign it to the fast core.
It's an example of synchronization. Synchronization, in my view, is the single most important concept associated with lots of, so parallelism is the fancy buzzword of lots of things being able to be done concurrently. At the same time, one has to synchronize at points in order to then move forward. And this is a very good example of synchronization. The plane can't take off till in fact, you've noticed, you know, somebody will come on and count the passengers in the seats, and they better have the right number, right? Right. And if this guy was hobbling on crutches all the way, you know, he hasn't gotten there yet, you know. So they have to wait for that synchronization point where everybody's on board and then they can take off.
Move forward.
That's right.
Right. So finally, I want to ask you, like someone out there who's considering going into engineering and is looking at all the different possibilities of engineering, why would it be a good idea for them to choose to become a computer engineer?
So first of all, why would they want to be an engineer in the first place, you know? Become a banker and they can have their 3 houses and have us pay the taxes that allow them to have those 3 houses, right? So I don't know you want to be an engineer at all. I guess the only reason for being an engineer is because what turns you on is solving problems, see? And you get up in the morning and you say, wow, I get to solve problems today, you know? And that's what engineers do, is solve problems. Now, problems are across the board. And your question was, why computer engineering? Because we've just scratched the surface of what computers can do. You know, so the analogy would be an iceberg. You know, we're at the tip of the iceberg. There are so many things that we can be using computers for that we're not yet. The fact, the work that you and I do, where we're trying to speed up the processing, we'd like to be able to predict a tsunami. Now, if the program, the tsunami is going to hit tomorrow. I'd like to know that today so I can get out of town, right? It does me no good to have a program predicting a tsunami and it takes 2 weeks before that program says, you know, the tsunami is going to hit tomorrow. Well, it's 13 days later, you know, when you find out, and you can just look at the debris and know that the tsunami hit. Or cure cancer. You know, if a program is, you get the symptoms of the person, and you start the program running, and 20 years later, you get the results of what to do to cure this guy's cancer. Except he's dead already, you know, because 20 years is a long time. So we want to speed up the processing. There's a lot of applications in that. Medical diagnosis, we're already starting to that, where you have the super doctor at, I don't know, MD Anderson in Texas, or Sloan Kettering in New York, or Mayo Clinic, I guess, or wherever, and you got the expert there. But the patient is over there. And with computers, and communication also, by the way, which is part and parcel of computers. In fact, I think that we are lucky to have an electrical and computer engineering department, because you get both the computing capability and the communication capability, and together it opens up the solution of a lot of problems. We have only scratched the surface of the uses of computers. It's already had an incredible effect on people's lives. You know, there's going to be a time, so I'd say 10 years from now, you won't have a driver's license anymore. Now you're going to need to have something to get you through security in the airplanes, but the point of knowing how to drive a car is going to be, you know, that's yesterday, you know, that nobody's going to drive a car. In fact, we're going to have it such that if you want to drive a car, your insurance is going to go up, because we can't trust you, a human, behind the wheel. We'll have a computer behind the wheel, say. We already have an experiment of that. Google, you know, has this car, which they,
right.
Yeah, but Google has got one car on the road. How about if every car is powered by a computer? So we still have to work out some kinks, but within 10 years, you will get into the cars, the back seat, sit down. Your weight on the seat will trigger the synthesized voice that will say, "Where to, master?" And you'll tell them, or tell it, it's a computer, it's not a him. You'll tell it, and then the computer will look it up in the GPS, which will have this other feature that we mentioned earlier about the traffic control. And then you can sit there and read the paper, and finally the car will stop, and you'll be in front of your house or in your driveway or whatever. I would say 10 years from now, insurance companies will not want you to drive a car, because you're a human and you're prone to making mistakes, whereas computers can be done much more precisely. That's what we're going to see. So there's a simple application.
Actually, there's a lot of applications of computer engineering, right? This is what I tell students, right? Why go into computer engineering? You can think of numerous applications.
It
right?
just, again, the tip of the iceberg. There is so many things that we haven't done yet, you know. There's a lot of things, you know, if you go back when I was a kid, you know, Dick Tracy with his, you know, and we said, now, you know, everybody has that capability. There's just so much more that that can be done that we haven't even. In fact, the computer engineers are not the dreamers. They're just people saying, "Oh, why don't we do this?" And then the computer engineer will provide that, and it'll be new. You know, you understand the difference between an engineer and a scientist. See, a scientist's job is to explain what is. An engineer's job is to create what never was. See, so, and computers is, you know, clearly the future. In fact, I went to graduate school to study electromagnetics. And I remember this guy saying, "Why are you studying electromagnetics? The future's computers." Now, I started graduate school, 52 years ago, you know? And today I'm still saying, you know, that in those 52 years, we certainly have done a lot, but we're nowhere near. We scratched the surface. There's plenty of problems out there where the computer can provide the impetus, the zest that will, you know, make solutions possible. So no, if a student wants to study engineering, which I hope that, you know, solving problems, if that's what turns you on, there's no better place than in computer engineering, because the problems are just, you know, they're plentiful, you know.
Professor Yale Pat from the University of Texas at Austin, thanks again for dropping by.
It's been a pleasure.